We are decoding fibroblast biology in order to create superior therapeutics. So fibroblasts are connective tissue cells. They're basically in every single organ in your body. They were long thought to be sort of innocuous bystander cells, just sort of structural. But over time, my co-founders and other researchers have found over the past 30 years that they are deeply involved in monitoring and sort of the local tissue microenvironment, both in terms of structure and function in controlling the immune system. And these are the cells in fibrosis that are actually causing, they deposit extracellular matrix, and they cause your lungs, your heart, etc. to turn very stiff and ultimately cause you to die. And fibrosis is involved in about 45% of all deaths. Our platform is based on the work of Dr. Michael Underhill from UBC. He's been working on these cells for about 30 years, and we take a biology-first approach. He identified a way to understand how these cells develop in the context of a mouse model, and we use that and cross it with different therapeutic animal models in order to see how the fibroblasts develop and then what programs are activated or dysregulated. For example, in fibrosis, we can see what programs are upregulated when the cells are depositing extracellular matrix and causing your organs basically to fail. This is completely unique. So our first indication, our lead indication, is a rare cancer called sarcoma, synovial sarcoma. There's really this huge unmet need. There hasn't been any major changes in terms of the therapies for this cancer in the past 20 years, and we're going to change that. The next indication we're looking at is IPF. It's something you might not have heard of before, but it kills more people than breast cancer and colorectal cancer combined. It's an increasing prevalence. A lot of it's due to COVID. So we are looking to actually reverse the fibroblasts and make them quiescent and improve outcomes. We're also looking at the tumor microenvironment specifically for really hard to treat breast cancers, and we're also looking at some rare fibrotic disorders such as scleroderma. So our differentiation is we have novel genetic models. Everything else is done basically in petri dishes. We feel like by using an animal model we'll have a much better understanding of the deep fibroblast biology and how sort of the dynamic interplay between the immune system. We've got longitudinal analysis, which is quite unique. And we're looking at different therapeutics, and really the deep understanding of the biology first rather than just the human data will give us superior targets.